Okay, now we continue the lecture. So far we have seen all the concepts that we need in order to understand several types of problems in geomechanics. The first type of problem of geomechanics that we're going to look at is to understand what is the effect of discontinuities such as faults and fractures in stresses, and also what is the effect of those stresses on the movement of fluids through rock. You can imagine that whenever you have a fault, many times, not all times, but many times, fluids will find that as a pathway, a preferential pathway for fluid flow. Many times you have hydrocarbon accumulations near faults because they also could be sealing. And for example, for unconventionals, we know that many rocks, they do have natural fractures, something that facilitates the production of oil and gas from very tight rock. So our objective now is going to be to understand what is the effect of those fractures on the stresses and also later on permeability. So the first thing that we have to do here is to understand how faults move on the earth crust. And if you see, faults are a sort of fracture. It's actually a large-scale fracture. I forgot to bring my rocks, but if you remember from the labs, whenever you break the rocks in shear, they form fractures at an angle, at a given angle. Those faults we discussed last Thursday, that you can map them. And I'm going to go very quickly through this, but if you weren't here on Thursday, please check the videos. I already uploaded those in YouTube. There are two quantities that we use to characterize faults. One is the strike, is the direction from the north to the intersection of the fault with the horizontal plane, and the other one is the dip. The dip tells you how steep the fault is. If you take a look at the block diagram, this is what you see. Again, the strike, direction from the north, that angle. Dip is the angle between a horizontal plane and the angle that you're looking at that could be a fault. That one over there. So we usually refer that strike and dip to something that we already know, and it's the geographical coordinate system. And usually we'll measure a strike clockwise from the north, and the dip will be measured from the horizontal plane towards the plane. So a dip of 0 degrees means a horizontal plane. Dip of 90 degrees means a vertical plane. And whenever we have those quantities, then we can use some other tools, like what we discussed are called stereonets, that instead of plotting something in 3 dimensions, you can plot that as a dot in this type of stereonet plots. Okay? We'll come back to this. Don't worry if you weren't here on Thursday. I'll explain that later on. But the main idea here is that when you have hundreds of fractures, you can plot all of those in a single plot, and you, looking at this, more or less you will have an idea about where those faults are. If you have faults randomly distributed in all directions, the dots will appear all over the place. But in nature, that's not all times the case. Usually you have the faults at the preferential orientation. So here you will see just mostly clouds around a direction over here, for example, and clouds around another direction. And that will tell you where most of the faults are located. Yes, Mr. Awa.
The angles that are over there, 90, 66, 30, are they angled to vertical or to horizontal? Like, does 90 mean horizontal or vertical?
Here in the stereonet plots, the stereonet tells you, it doesn't tell you what is the the fault plane itself, but it tells you where the intersection of a line perpendicular to the plane is on a hemisphere projection. So if you imagine this as a hemisphere and you have this plane over here, that point is the dot. So whenever this is 90, that means a plane dipping at 90 degrees. And look, if I get it to be less deep, this one is going to move from here through there, and over there, the dip is going to be 0 degrees. So we say that dip is 0 degree when it's horizontal, 90 degree when it's vertical. And the location of the dot around these circles is going to tell you what is the strike of the fault. So it's a very convenient way of plotting the orientation of planes in a simple plot. And whenever you have hundreds of faults and you want to map all of them together. Okay, so we know now what faults are, and we know their direction. And we said that faults are caused by stresses, and they are very similar to shear fractures, right? So what we're going to do now then is we're going to discuss about what is the strength of faults, or what is the requirement of a fault to form. So very similar to what we have done before. We're going to use the same equations. If I gave you a piece of rock that was already fractured, what do you think is going to be its unconfined compression strength? The rock is already fractured. You remember that silly example I did with the tensile strength, or with a fracture in one direction? Tensile strength was 0, right? Perpendicular to the fracture. What do you think if I gave you a rock which has a fracture like this, and I want to load it in this direction? What do you think is going to be the unconfined compression strength? If I have no confining pressure, no stress in the other direction. So you remember here we have a line. Usually the line is going to tell you, the intercept is going to give you unconfined compression strength, and the slope is going to give you a friction coefficient. So if I have a block which is already broken, the unconfined compression strength is going to be 0, right? It's going to be 0. There is no unconfined compression strength as long as I don't have any stress in the other direction. So this is going to be a line in the case of faults. And remember that faults, it's a rock mass at the large scale, and it's already fractured. So here I'm just going to have a line where sigma 1 is equal to Q sigma 3. And notice that when I add now a stress in the other direction, now this fault is going to be able to resist some shear stress, because now there is a normal stress on that plane. So it's the same thing, you know, if I get this and I get it close to this and I drop it, it's going to fall. But as soon as I put some normal stress on it, it's not going to fall anymore because of friction. It's the same thing with the rocks. As long as you have a stress, a minimum principal stress in the other direction, an effective stress, this is not going to slide anymore. And we're going to do a cool experiment about this Thursday or Tuesday. I'll see how far we get today through this. So as a conclusion of this, then at the large scale on the Earth's shallow crust, the strength of the surface is just going to be dictated by that law. As simple as that. And if we remember what was the ideal orientation of a shear fracture as it is loaded to failure, I'm going to just repeat the same plot again. This is sigma 1. This is sigma 3. Do you remember what is going to be this angle over here? We're going to call that angle, let's call it beta, okay? And beta was equal to 45 degrees plus the friction angle divided by 2, where the friction angle was the arc tangent of the friction coefficient, and I don't remember the equation for Q, but the friction angle is a function of Q. Okay, so if you know what is Q, you know what is the friction coefficient. Something very important to notice over here too is what is the magnitude of this Q. So Q, this equation I do remember, you can calculate it as 1 plus sine of the friction angle divided 1 minus sine of the friction angle. And for example, for a friction angle equal to 30 degrees, what is going to be the sine of 30? You remember that? So 0.5, so this will be 1.5 divided 0.5, which is going to be equal to 3, okay? And I like that you remember this number, okay? 3. It's easy number to remember. What that means is that sigma 1 can be more or less 3 times larger than sigma 3. So as long as you have a minimum principal stress which has a value like say 1000 psi, you can put 3000 psi over here and this rock is not going to fail, it's not going to move. It's a solid and it resists an isotropic state of stress because of friction. So that leads to something which is called stress anisotropy. So that means that stresses can be different in different directions, and that is going to be stable. And we're going to use a lot this coefficient 3, and we're going to also use a lot the beta that will result for 30 degrees. So if friction angle is 30 degrees, that will result in an angle beta of 60 degrees. So with this knowledge that we already knew, we're in conditions of telling what will be the ideal orientation of a normal fault in the subsurface. So let's go to a real case now and imagine that we go to the Permian. Oh, by the way, guys, raise your hand if you want to go to San Antonio to visit a fracturing path. 2 people, 3, no one else? No? You don't want to go to San Antonio? It's going to be a cool trip. We'll take a bus, we'll go all together. No? I see some people that are not very motivated. But anyways, if you want to come, you're welcome. I was talking to a guy from EOG, and he was saying that he'll be delighted to invite us and to have us in San Antonio to go to a fracturing site in the Eagle Ford. Okay? So let's imagine that we go to the Eagle Ford here, and we are in a location. Most of Texas is under normal faulting stress regime. Okay? So the minimum principal stress is smaller than the vertical stress, and of course smaller than the vertical stress. So somewhere over here I'm going to have the vertical stress, and you're going to be drilling somewhere over here, and our objective is try to understand what are going to be now the ideal orientation of a shear fracture or of a fault at this location. What is going to be the ideal orientation of a hydraulic fracture? And now I want you to tell me, well, let's for a minute, let's make this a little bit easier, okay? And let's walk out of the Eagle Ford, because there the orientation of SH mean is going to be at an angle from the east. But just to make this simple, let's assume that the north is in this direction and the east is in this direction. So look, SH mean is acting in direction east-west, right? So tell me what would be the strike and dip of a hydraulic fracture at this location, the ideal orientation. So strike, dip. So who can tell me the strike? I'll give you some extra points. It's been a long time we don't do extra points.
Strike would be north.
The strike will be north, okay? And can you tell me that in strike convention, the azimuth convention? It's going to be 0, 0, 0, okay? So that's going to be a plane like this, right? And it's also going to be a vertical plane, right? So what is going to be the dip? It's going to be 90 degrees. Okay? So if I were to draw this hydraulic fracture, let's see if I'm successful at doing this. Coming out of the paper, it's going to be something like that, right? A vertical plane like this. Strike, it's aligned with the north, so it's 0. Dip is 90 degrees, so this angle is 90. Yes?
How do you know that it strikes north?
Because it is perpendicular to the minimum principal stress. Look, minimum principal stress is here. Okay, I said this in words, but I didn't write it. We're in normal faulting. So normal faulting, that would mean that this one is bigger than that one, and that one is bigger than this one. So this one is the minimum principal stress, S3, and therefore hydraulic fracture will be perpendicular to that one. If we had this one coming from direction north-south, it would be like that. Okay. All right. So we're good so far? Okay. Now I want you to tell me what would be the ideal orientation of a fault. I want to know what is a strike and what is the dip for this same location. So this one we know very well, okay? Hydraulic fracture, relatively easy. What about the ideal orientation of a fault? And a fault, remember, is the same of a shear fracture. Any guess?
Would the strike be 0 and
it's going to be exactly the same as that, okay? And so you said strike would be
I said 90.
90? No? Nathan, you think differently?
I think it's 90.
What do you think it is then? My plots over here were 2D. Probably I should have done this 3D, okay? So let me fix it slightly. If now we have a 3D plot, this is going to be sigma 1, and this is still going to be sigma 3. And this one over here is going to be sigma 2. Notice that in the lab, your sigma 3 and sigma 2 were the same because you have a cylindrical sample. But in nature, in most cases, there is a difference between this one and that one. The shear fracture is going to be always oriented in such a way that the plane of the fracture is in the same direction of the direction of the intermediate stress sigma 2. So this line is contained on that plane. And another thing of looking at this is by seeing which one is the biggest and in which one these blocks are moving. So by definition, sigma 1 is larger than sigma 2 and is larger than sigma 3, right? So how do you think these blocks are going to move? Like this one is called the hanging wall, this is called the foot wall. So is the hanging wall moving according to this state of stress? If it were to move, will it move down or will it move up? It will move down, right? And if you were pushing like in this direction up and this one down, this is the maximum stress. This one will go up, this one will go down. But notice something else. It's not only about things moving up and down. This block is also going to move to the left, and this one is going to move to the right. And it's not going to move in this direction. So why is that? Why it moves to the left? Because it's going through that plane, but also because it's trying to do work against the least principal stress. Why would it do work against sigma 2 if that's larger than sigma 3? It will break in a plane so that that plane, when it moves, is going to move down according to the maximum principal stress in that direction, and it's going to move against the minimum principal stress. Always do work against the minimum principal stress. So very similar to the case of a hydraulic fracture. A shear fracture always is going to try to minimize the work done after it fails. But it's a different kind of failure, and it's at a different angle. But also it's going to do work against sigma 3. All right? So now, based on this plot, can you tell me what is going to be the strike and dip of faults in this location? While you think about that, I'll continue doing my art over here. Strike 0, 0, 0. What about the dip? There is one missing piece of information. I'm going to say that the friction angle of my earth section is 30 degrees. 60 degrees, and in which direction? So what you're telling me, so what you're telling me is the strike is going to be like this, right? So it can be anything like this. So it's going to be this, or it's going to be that. That one? And why not this one? Okay, but you know, in order to be in equilibrium, there should be another one over there too, which is the same. So actually, there are two solutions. There are two possible solutions. There's one that is going to be like that, and one which is going to be like that. So here we will have either 60 degrees deep into the east, and that one is going to be a fault which is somewhere over here, and there is another solution which is going to be 60 degrees deep in towards the west, and that one, let's call this one 1 and this one 2. This one is going to be another fault which may be somewhere over there. So this one is number 2. But in general, your normal faults that you will expect at this location are going to be in this section. And let me continue. If this were to be the pay zone, probably if we have this one will go down. So probably we'll have something like this. And I made this one a little bit more complicated, but let me just leave it like that for now. Okay. Normal faults. Okay. They are very steep, and the angle is from this plane, the plane of the vertical stress, 60 degrees. Or also you could measure it from this plane, the plane of S1, 60 degrees towards that plane. So those are the kind of faults that you will expect on this condition. That would be the ideal orientation. So now let's take that concept and extend it to the other types of faulting regimes. We have 3 faulting regimes, you remember? We have normal, strike slip, and reverse. So, but it's exactly the same thing. So let me repeat that. Here we're going to have normal faulting. I'm going to repeat what we have done before. I'm going to make the drawing a little bit simpler and just going to consider a prismatic element at some depth. If I have SB in this direction, I have SH mean, and I have SH max. Again, the orientation of a fault at this location, if I assume a friction angle equal to 30 degrees, it will be very steep, about 60 degrees, and the strike is going to go into this direction, right? Where I'm assuming in this case this is the north, this is the east, and this is the, just for this case, okay? And this one is 60 degrees. Strike 0 degrees, deep 60 degrees, in this case towards the east. Let's see the case of reverse faulting, which is going to be the maximum principal stress in reverse faulting. You guys remember that? Which one? SH max, that one. Minimum principal stress is going to be now SV, and intermediate stress is going to be SH min. So look, this is SH min, but it is the intermediate stress, right? So reverse faulting. Okay, what is the plane at which you will expect a fault in this location? So let's try to solve this all together. Using the same concept that we saw before. What is the maximum principal stress in this case? SH max, right? And the minimum? SV, right? And this is the intermediate. So if this is the plane of the maximum principal stress, and we're going towards the plane of the minimum principal stress, this fault should be located at an angle that it is at 60 degrees from this plane into that plane, right? So it will be something like, if we start this the plane of S1, we'll go 60 degrees into that plane, and that's going to be the fault. So what is going to be the strike of that fault? You can tell me a number, right? Now we can tell numbers about that. So it's the same coordinate system as the other one. 90 degrees, very well. And what about the dip? So I'm going to write it, before I draw it, I want you to picture this in your head. 90 degrees, and what about the dip? So we said 60 degrees, right? So I'm going to draw the plane. That I did with the paper. This line I'm drawing right now, that's the line of the strike. And what is going to be the dip? 30 degrees towards the south, right? So that will be the orientation of a fault in a thrust regime or in a reverse faulting regime. Notice that it will be much less steep